Hello and welcome to this week's edition of the Applied Deep Learning course. Today we're going to take a look at neural networks, optimization and backpropagation. Before we dive into the topic, I would like you to take a moment and head over to Tuval. I created a small quiz for you which recaps on the subject of topics that we covered last week. Take the quiz, which should just help you to remember the topics we talked about last week, and then come back to this video, to this moment, and continue with the lecture. I gave you a bit of terminology, and we talked about artificial intelligence being somewhat the marketing term almost for this encompassing field of everything that has to do with some sort of intelligence, where computers are involved and where even some things that maybe previously weren't thought of as the other way around, where back then people thought, oh, this is artificial intelligence. We nowadays say, well, this isn't artificial intelligence, so let's try to avoid this term altogether and rather go into the topic of machine learning, where we try to use data to answer certain questions, where we try to extract meaningful patterns that help us to understand our data to a better extent. For example, with simple linear regression, and with the two subtopics that we will mostly deal with, which is representation learning, where we're not using the entire data, for example, what we have with KNN, where we just store all samples, but in our case, we try to extract a meaningful representation and then use this model, the efficiently stored parts of information to answer these questions, and then with one particular subsection of representation learning, which is deep learning, where we use neural networks and typically stack them with lots of layers, and then we can call them deep learning. I would also like to recap from last week how I presented to you how machines can learn in general. The first ingredient is a model, which is a set of computational rules that take an input, process it, and produces an output. That is the model. The second part that we needed was a cost function, also sometimes called a loss function, where we basically try to answer the question, how good are we doing right now? And ideally, this loss should be as low as possible. And to get to this point where we have a low loss, we need a third ingredient, which is an optimization function, which basically is nothing but telling us in which direction should we go, what should we change to reduce the loss to get better. So one question is, how does a model work? How does it take some computational rules and perform a computation on any sort of input? Well, we typically start with some data. So in this example, for example, we have images of cats and dogs, just one cat and a dog. So our input data, and what we often have is an associated label. In our case, the first image depicts a dog, the second image depicts a cat. Now what we do is we take that input, which we can represent as a vector or as a matrix. If we talk about colored images, we typically talk about a three-dimensional space where we have X, Y, and the color channel information for our images. And then we feed this into our model, which is then asked to produce a certain prediction, some output. In this case, it can say whether it thinks it's a cat or whether it's a dog. So the idea would be that by taking a look at many examples of cats and dogs, it will eventually be able to take a new image, this example here, and be able to say, well, this is a cat or a dog. And this process is what we call inference. So the model typically does this in two different steps. The first step would be to take the training set, so the images that we separate away and that we show to the model in order for it to tune its parameters, to learn how to do the task that we ask of it. And then the second part is the inference, where we take images from our test set, images that the neural network has not seen before, and ask it to make a prediction. If the network outputs a probability, in this case it could say, well, it thinks for a probability of 0.7 that it's a dog, and with 30% probability it's a cat, then we would call this model a probabilistic model. And that kind of model is the most common one that we will be talking about. So one question is, how can a model work on unseen data? How does that work at all? I mean, if I teach you French, you're not all of a sudden able to speak English. So there are some restrictions on our data that are important to understand in order to make this work. And first restriction is that both datasets, or our dataset that we split into a training and a test set, must have the same distribution. They must come from the same language. They must show similar objects. They don't have to show the same object, but the distribution, the underlying distribution, must be the same. And the second the requirement here is that two sets have to be independent of each other. Otherwise, we'll have some information leak from the training set into our test set, and then the results wouldn't be very meaningful. These two requirements are often abbreviated as IID, independent, identically distributed. So as we can see in this example here, we have the white and the purple dots, and they form two clusters, but we randomly drew samples, so we can actually learn this distribution of these two clusters that we can separate, in this case, linearly with a line. So the question then is, does our network generalize? So if we train it on one thing, does it work on another one? If we stick to this principle that the subsections of our dataset are independent and identically distributed, it should generalize. But of course, there are always limits. That is one example that I've been working on. So I trained my neural network on music scores to do measure detection. So basically to detect the basic structures, the basic elements of music. And then I tried it on a different set of music scores. In this example, scans of old scores. And as you can guess, it only worked to a certain extent, because the network learns the underlying principles, it learns the underlying distribution. And one thing that clearly violates this set here is, for example, the color information, that it was only ever trained on black and white images, and all of a sudden we give it a color image, well, then it will probably not work as well as you might expect it to work. I also already told you this last week. I want to tell you the story again, especially with regards to dataset, that you have to be very careful crafting your dataset and making sure that your dataset is well prepared, because in this paper or in this research line, they tried to distinguish between good and bad skin lesions, and whenever it was a malicious one, they had in the underlying image a ruler to kind of learn how big the object in question is. And then it turned out that you got a data set that was not identically and independently distributed, because all of the bad examples had this ruler in the dataset. So the image classifier ultimately was a really good ruler detector, which was really good at saying whether this is a ruler or not. But once you showed it images of malicious melanoma without the ruler, it immediately said, well, this is a benign thing I don't care about because I don't see a ruler. So as you can imagine, that wasn't very successful, but they figured it out, they fixed it in their data, and then they were able to train this very well. Typically, we talk about different classes of models. One class of models is a so-called discriminative model, where we learn decision boundaries, where we try to figure out where the probability, the highest probability of one class changes to the highest probability of a different class. So we say, like in this example here, it can be red, blue, or green, and at a certain point we say, okay, well, now it's more likely to be of the blue category than of the green category. A different class of models is a generative model, where we typically learn class conditional densities, where we learn the underlying distribution directly. This is most often the case when we work with unsupervised learning. When we talk about the outputs of a model, we also can typically distinguish between two different classes here of things that have a finite number of outputs, or where we have a continuum and potentially an infinite number of values that we can produce. One thing where we only have categories, that will be classification. Whereas if we have an infinite number of potential outputs or a continuum, we typically call this regression. Let's talk about neural networks. Neural networks have been invented back in the 70s. They first had this idea of mimicking how our brain works, and they tried it, and it turned out that it didn't work very well, because back then the computing resources weren't that powerful as what we have nowadays, and also some of the approaches that we're using nowadays haven't been developed to the extent that they're developed today. So the neural networks have actually seen quite interesting development of this hype back in the 70s, then the so-called AI winter, where no one was doing neural networks, no one was doing this sort of research, and then it surged back into what we have nowadays, which we can call another AI spring if you want. So neural networks at the core are inspired by the way how the human brain or a brain basically works. And a brain consists of neurons, which is the smallest unit, basically a small computer, if you want, which takes inputs from other neurons through the dendrites. And those are the inputs, so they are connected to other neurons. And then all of these inputs are merged and somewhat processed in a chemical process, and then it activates or it doesn't activate and propagates that output through the axon to other neurons. So an artificial neuron tries to do a very similar thing in a very simple way. So we have certain inputs, for example x0, which can be any real valued number, and we process that, for example, by multiplying it with a certain weight, and then taking that input and all other inputs, x1 and x2, computing the sum, applying an activation function, and then outputting that to the next step. That's basically an artificial neuron, and if you put multiple neurons together, we get something that we would call a neural network. A single neuron, in our case, would just be a linear classifier. And the goal of machine learning, and especially of deep learning, is to use these neural networks that we can construct out of these single neurons and try to find good values for these parameters here. So W0, W1, W2, and also the bias term, to kind of produce something meaningful. So if you think about a linear classifier, we want to find the line that separates two classes from each other. When you combine these neurons into a neural network, this is what we call a parametric model. So neurons are controlled by these values, the weights and the bias term, and they are the parameters. They are the failures that we can tune to get the best output. Whatever that may be, we can actually change these values for it to be a universal approximator of any function. So if we want to classify images, it can be an approximator to learn to classify images. The activation function is also called nonlinearity and is an essential part of a neural network. Why do we need an activation function? If you think about this for a second here, we just multiply it with a matrix here with W and then add a term here, B. You can actually represent this as a single matrix multiplication, and if you don't have any nonlinearities in your model, you can actually, and you apply the same thing a second time, you could actually merge those two matrices together and solve this with just a single matrix multiplication. So all of your computations would collapse. Therefore, you need some nonlinearities in your network to kind of keep them separated. And that's what our activation function is fundamentally doing. In other words, if you can think about an activation function about something that tells the neuron whether it should fire or not, whether it should be active or not. The most popular activation functions include the sigmoid function, which is biologically inspired, the ReLU, and the leaky ReLU. So sigmoid, as I just said, is inspired by nature, so we can find this kind of sigmoid function in many natural neural networks that are operating as well there. But typically when we talk about artificial neural networks, they do not work that well, so you should probably avoid them. Often you can see that they saturate, and then the thing that you want to go through doesn't go through as much as it should. So typically sigmoid activation functions should be avoided. The ReLU function is the most efficient one. As you can see, it's a super simple function. It just takes the maximum of 0 and x of the input. So it just cuts off everything that is to the left of that is below 0, and otherwise just lets the signal go through when it's positive. And that is very efficient to compute, as you can see here. It's just an if statement basically, and it has certain issues with dying neurons. So when you think about a signal that goes to the left of the y-axis, so that is negative, and you don't get any signal at all, well, it doesn't propagate any information. So people have come up with this idea of a leaky ReLU, where we also propagate at least a small signal when we have a negative input here. So leaky ReLU tries to mitigate this to a certain extent, and especially when you think you have dying neurons, so neurons that sort of at a certain point are no longer firing at all, because whatever input you feed it in, it just computes something negative and then it's 0. Then you have a dead neuron. If you think you have that in your network, you might try leaky ReLU, but it's more of a trial and error thing, I would say. So the basic recommendation to take away from this is, and by the way, there are many, many more activation functions out there, and this is still an active field of research where there are lots of other activation functions that have been proposed. And in one paper, they claim that this activation function works much better on that problem, and they show some interesting properties why it's the case. But I would say as a practitioner, you start with something like ReLU, and then you can still try to figure out if different activation functions should be used and help you to get to a better result. Most often, the activation function is not the most critical point in your neural network. So, I've already thrown this term around a bit, but let's make it a bit more formal. A neural network consists of several neurons that are connected to each other, And if they are arranged in a certain way, we call this a feed-forward neural network. In this case, we have multiple parts of our neural network, and all neurons that appear at the same kind of, that share the same inputs and outputs, we call that a layer. So in this case, we have one layer that takes some inputs, so those are our input neurons. Then we have one layer, we have a second layer, and then at the end we have the output. And those layers in between the input and the output is what we usually call the hidden units. So a neural network, in theory, is a universal approximator. They can approximate any function, and it has been shown that they can, like in a theoretical way, really do this. So the question is, if you have something that is so extremely powerful, how do we get it to do something meaningful? Well, it's not just a neural network like the one we've seen before, but typically there are many more components in a neural network. And to not lose oversight of this, we usually structure a neural network into two parts. One would be the so-called body of the network, where most of the time we extract some features, and the network learns to extract meaningful features from our data. And then we have our second part, which is the so-called head, which is, depending on our specific problem, doing something different. For example, we can have a classification head which outputs categories, or we can have a regression head which outputs some real valued numbers. So let's talk about the cost function, aka the loss. It basically boils down to the question, how are we doing right now? We have this parametric model which operates on this space of values that it can tune. So we have to kind of figure out how we're doing at the moment. So depending on the problem that we're trying to solve, different loss functions are required. One option could be the so-called mean squared error, where we take the difference between the value yi. So that is the truth label of our input, and then we compare it to the predicted value for that input, so yi hat, and we compute the difference, we square it, and then we sum over all our input samples, and that gives us one value, which is the mean squared error. Similarly, we could also take the absolute value, the difference between those two, and when we compute this loss, we typically use it for regression problems where we have like different values out of a continuum that you can compare to each other. If you can't compare the values, because like think about the difference between 2 and 3 is the same as between 3 and 4, but when you have data that are categories, what is the difference between cat and dog or car and tire? It's hard to say. That's why for classification you typically use a different loss which operates on probabilities of certain classes, and we call this the cross entropy loss. And this is the formula how to compute it. Don't be scared, it's not as complicated as it might look at the first sight. If you just plug in some numbers, you will see it gets quite clear what it does. So let's put in some numbers. What it basically does is it takes two parts here. The first half is yi log of the prediction. So whenever the thing should output something, we compare it to what it actually says. And the second part is kind of the penalty of when it should not predict it, like when it's not of the same category, and then we penalize it with something. Let me show you with some numbers. So if our target, which would be y, and it has 4 values, 0, 0, 0, 1. So we know that our example comes from the 4th category, whatever that may be. And what we have here is an encoding. So we have, for example, the category cat, dog, car, and I don't know what the fourth category is, truck. So in our case, it's a truck. Then we can have good predictions or poor prediction, and those are probabilities. So if the prediction is with a very high confidence saying the same category, then we have like low values in the first few categories and a high value in the last one. So when we just compute that formula with these values, we get a cross entropy loss of 0.04 for the good prediction and 1.39 for the bad prediction, which just guessed that it could be any of those four categories. And that already gives you kind of an indicator, oh wow, this thing looks quite close to what it should predict. We get a low loss, and if it's just doing putting out some garbage or some random numbers, we're getting a high loss, which is exactly the kind of information that we want to have here. Like, we're asking the question, how good are we doing now? So the loss function that we compute with any of these functions usually can become a quite complicated surface. And let me rephrase this in a different way. We have millions of parameters in a neural network. We can have tens of millions of parameters. And each value, each parameter is one axis that we can change. So if we have two parameters, it's a two-dimensional surface that we're navigating on. Now, if we have millions of parameters, this loss function becomes a surface in a very high dimensional space. And we typically don't have that many samples for everything, so it can be really complicated to navigate this loss function. Ideally, we want to get down to a point where we have a very low loss, but as you can see in this image, we might end up somewhere if we just try to find the lowest point that is not ideal. So that is our loss, and that is our loss function. And if you visualize it, it becomes sort of a landscape that we're navigating through, which is a very important thing to remember for the third part of our parts that we need to train a machine to do something useful, which is the optimization. You've guessed it. So the question now is, if we have this really complex surface, which is kind of hard to navigate through, and we have millions of parameters, how do we get to any point where we have a low loss? Because we could start changing the first parameter, we could change the third or the 50,000th parameter. How do we know where to get there? And this is where our optimizer comes into effect. What it does is basically we try to do something called gradient descent. And for understanding this, gradient descent is a non-linear optimization algorithm that is really, really popular, and you will find it everywhere. And you can imagine this. The simplest explanation that I ever got was that you are in the mountains and you're hiking and you're trying to get down to the valley, which, you know, the mountains are our loss surface and we're trying to go down to the valley. So how do we do this? As humans, we kind of look around, we try to find a path, and then we walk into that direction. And we have something very similar that's happening here as well, but with one problem. It's like hiking with a sack on your head. So we don't see anything around us. And mathematically speaking, we'll talk about this in a second, but the problem that we now have is that we are in the mountains and we don't see where we are going. What is left to do? Well, that's the trick. We try to find a small optimization. So what we basically do is we try to scan the nearest surrounding. For example, if you take your feet and then you spin around in a circle, you try to find the direction. So you just do a 360 degree spin, and you try to see, okay, where the steepest descent is, and then you find it, you take a small step into that direction. Once you've done that, you can repeat the very same operation. Again, scan the surrounding area, see where you have the steepest descent and take a step into that direction. Will you end up in the valley, in the lowest valley? You might not, but at least there's something we can actually compute with a computer. So let's talk about gradients, because this is the fundamental idea with gradient descent, and I've already given you the basic idea of being this landscape that we navigate through. So let f be a differentiable real-valued function, in our case the loss function, the mean squared error or the cross entropy loss. Now you can compute the partial derivative f of xi with respect to xi. So we can say, okay, if I change the parameter xi, what is the difference that it makes for my function here? If I just change this one value fi. And now what we can do is we take the partial derivative not just of xi, but of x1 or x2, but of all of our inputs, of the entire x, and we compute the partial derivatives for all of our inputs, for all of our parameters, and then we can kind of determine how fast our loss changes with respect to every single parameter of our model. And then we take one step into the direction that brings us down furthest and fastest, where we have the steepest descent. So we compute this gradient, and then this kind of points us in a direction which we have to take a step. So gradient descent is the iterative algorithm that operates on the loss function. So we compute the gradient, we kind of at a certain point in time, we take our parameters theta, and then we compute the loss of some input, and then we can say, okay, now I know when I change my parameters, I know how every single parameter change will affect our loss function. I can do a so-called update step where I take this gradient, this direction, and multiply it with a certain value, with a small so-called learning rate, and then we obtain a new set of parameters and we can repeat the same process. Again, this requires that our loss function is differentiable and real-valued. There are a couple of terms that are flying around that you will often see and that are sometimes not clearly defined, so people use them interchangeably. That's why I want to state the clear definition for them at this point. So there is something called stochastic gradient descent, which is the simplest thing that you can probably think of. So you take one sample, you feed it through your network, you compute the loss, you compute the gradient, and then you update it with just one input sample. You can also do this with all of our input samples that we have, with our entire data set. That would be called batch gradient descent. The problem though is with batch gradient descent, it's quite computationally hard to fit all of this into your neural network. That's why it's usually not done. And the middle ground between taking your entire data set and just taking one sample and doing gradient descent is called mini-batch gradient descent. And this is the most common case that you will find in neural networks, in applied deep learning, where we take a set of samples, for example 32 or 64 samples, we batch them together into a so-called mini-batch, and then we compute the loss on this mini batch. So some of the challenges that we face when we do gradient descent is finding the proper learning rate. How big should our step be that we take into the direction? Because if you can imagine that if this is kind of too small, we won't get anywhere. If we take too large steps, we might fall over, or we head into some direction because it was just like a small like a small valley or something, and then we're already on the next hill. So, and of course, we might also have some critical points where we drop into local minima, which we would ideally want to avoid. I'm fairly certain that you're familiar with these terms, so let's just quickly go over them again. You can have something called the global optimum, where we get the lowest possible value of our function. In this case, we just have this very simple function. So we would ideally want to end up in this first valley here, but it might happen that we end up in a local minima, which is nearly as good, not as good as it gets, but it's acceptable. And if you're doing poorly, you might end up in a local minimum that is not performing very well, that we would like ideally to avoid. So critical points would be one of these local minima. And the question is, do we ever get there if we have millions of parameters? And the answer is no. We typically do never get to one of these critical points because our loss surface is so immensely complex that we can always kind of find a way out, that when we change this single parameter here, it might change something somewhere else. But that's fine, because as you just saw here, there are lots of local minima where we're absolutely fine with halting. So when you train a neural network, you typically see something like here on the right side, where you see this error rate, where it kind of goes down for quite a bit, and then it kind of jitters around a certain low value. But it doesn't get any better or any worse here anymore. When we do gradient descent optimization, there is one really important concept called momentum. So if you visualize your loss surface as a canyon, and you're standing on one side of this canyon, then you have a very steep descent in one direction, which is kind of downhill this canyon, and then back up on the other side. So if you take a small step, you kind of decline down this canyon. But in our mathematically speaking, these canyons, it's really hard to say how wide they are. So what can happen is that if we pick a poor learning rate, that we take one step, and that step is so big that we end up on the other side of the valley. So what will happen there? We'll take a look around and we'll realize, oh, we have to go the opposite way and do a nearly 180 back. And then, as you can see here, so when you take this surface here, we're spinning back and forth between these two sides of the valley, of these walls, which is really bad because it can take us a very long time to get down to the lowest point that we want. Momentum is there to help us. Momentum is a sort of small memory that we take along, where we know, okay, how fast are we going in a certain direction. So if we take one step in a certain direction and the next step is in exactly the same direction, we can actually start to walk faster, because it's kind of empowering us to continue walking in the same direction. If we realize that first step goes in one direction and the next step goes in exactly the opposite direction, we should probably slow down our steps and make smaller steps to figure out what's going on here and not jump from one part of the canyon to the other one. So what we compute here is a certain velocity, and we add that velocity to our update operation. And that can help us to solve this issue when we are talking about these canyon-like loss functions. There are also tons of other optimizers, and as with the loss function and activation functions, this is something that is under active research, and you will definitely, if you go into the literature, find conflicting information, where one of these adaptive algorithms claim that they're performing very well, and then the next paper might come up and say, well, it sort of performs well on this task, but at the risk of certain overfitting or not working well on other general types of functions. And nevertheless, let's talk about these adaptive algorithms, because for many problems they actually work very well. For example, ADAGRAD, which adapts the learning rate of the parameters. So we kind of have low learning rate for frequent events and a high learning rate for infrequent events, which, if you think about it, makes sense. That if you see something more often, well, you're not gaining that much information of that event anymore. But if you have a really rare event, you want that to really propagate through your network. ADA delta extends that and aggressively decreases the learning rate as well. RMS prop is very similar to ADA delta, which was almost simultaneously invented by someone else. So these two are pretty much the same. ADAM is a really popular one, which has become sort of the default learning adaptive algorithm for gradient descent, which adapts the learning rate and also stores the decaying average of past gradients. So it's a similar idea to this momentum, that we kind of have a memory of knowing where we went in the past and then adapting our learning rate accordingly. And finally, AMS-GRAD adapts the learning rate and also computes some additional things to also make sure how these parameters work. But I have to say, it's really hard to give a good recommendation of which one of these works best. And there's been a really nice and really interesting work by Mr. Ruder, and he made this really nice visualization that I want to share with you, is where he kind of constructs a loss surface and then he lets loose a bunch of different adaptive algorithms and then just tries to see how they perform on this. And you can see that these adaptive algorithms, they usually go down very fast, whereas stochastic gradient descent without any momentum is bouncing back and forth. So in the right figure you can actually see this quite well, that the red dot kind of gets to this point where it doesn't move downhill anymore. Momentum does, but it takes quite a while. But coming from a practitioner's point of view, I would still probably start with simple, plain, vanilla stochastic gradient descent with momentum as a default, but feel free to play around with any of these adaptive algorithms. Just today I heard about a paper where they're trying to learn an optimizer function, which is a super weird idea, but I mean, why not? In the time of machine learning, people are trying to learn all sorts of things, and this is again an algorithm, so why not try to learn the best optimizer from some data? But you know, that actually leads us a bit too far. Coming to the next big question that might arise when you talk about this. How do we compute this gradient of our loss function? We've heard about this being an immensely complex function with this really complicated surface. So how do we compute this effectively and efficiently? Well, there is one key idea here, is that the function that we're trying to optimize is composed of other functions. And if it's composed of other functions, we can try to compute something for these smaller parts and then put it all together. So the loss function is again a graph for which we need the derivatives, but we're not computing the loss and the gradient for the entire graph in one go, but we're actually breaking it down into smaller parts and then recursively apply the chain rule to compute the derivatives for each part of our network. So if we have simple functions, and our network typically is composed of just simple functions like multiplication or an addition or maybe a maximum between two values. So if we take f1, 2, 3 here, being defined as the multiplication, addition, or the maximum between two values, the respective partial derivatives with respect to one or the other input are for the partial derivative of the multiplication with respect to x1 is just x2, same vice versa. For the addition, it's 1. And for maximum, we need this kind of if-else here to say whether it's 0 or 1. But you can see here, computing a partial derivative of this simple function is really easy. So all we have to do is combine this, decompose it, compute this, and then put it back together. So let's take a small sample expression, a function e, which takes two inputs a and b, and then we compute the function a plus b times b plus 1. So we have two inputs, and we can draw this as a graph and decompose it into the two sub-expressions. So the first sub-expression would be c equals a plus b, and the second sub-expression d would be b plus 1. And then we join these two with a multiplication. A very simple function. So we can compute this. Now let's just put two numbers in there and see what happens. So when we input the number a equals 2 and for b the number 1, we can actually propagate this through our network, and we get c equals 3, d equals 2, and e equals 6. Now we can do backpropagation because we know the steps that we took to get from one function to the next function. So our function e is the multiplication of c and d, and e had the value of 6. So now we can compute the partial derivative of e with respect to the left part, to c, which is 2, and the partial derivative of e with respect to d, which is 3. And then we repeat the same for the next layer down there. We have the simple addition. C was just adding a and b. So the partial derivatives for both sides are just 1. And then we had another addition of d, which also gives us the derivative of 1. So now we can compute the partial derivatives here of the function e with respect to a by just traversing through this graph and multiplying all the gradients that we find along the way. So when we want to say e with respect to a, it's kind of walking downhill. It's the c with respect to a and e with respect to c. So it's 1 times 2 equals 2. And that's our gradient for a. And we can do the same thing for b. In our case, b here, now we have two branches that we have kind of to follow both of these branches through. So it's 2 and 3 multiplied by 1, going through the partial derivative of c with respect to b and d with respect to b, and which gives us the final result of 5. That is backpropagation. That's the entire magic. And there are some tricks that we usually apply for backpropagation to be more effective here. So you've already just seen this kind of going into two branches and then having to compute all the paths through our network. This can kind of lead to a combinatorial explosion. But there is a trick how we can solve this quite nicely, which is called path factorization. So what we can do is we kind of factorize this and compute the partial derivatives for all paths, which gives us one really nice benefit, that we only have to traverse through our graph once. And this is then called forward mode or reverse mode differentiation. So we compute kind of this for the entire path for all different things, and it's a really nice way, an effective way how we can do this. So instead of summing over all the paths explicitly, we compute the same sum more effectively by merging paths back together at every node. So we can kind of only visit each node exactly once, thus being very effective even for large neural networks. In practice, when we talk about deep learning libraries like TensorFlow or PyTorch, they internally know this graph. They build this graph, and that allows them to do exactly this operation. For PyTorch, for example, what it does is it computes on the forward pass the operations that it did. And then this allows so-called, I think it's auto backprop, where it kind of can compute the backwards propagation for each of these functions. As we just did here, we know that partial derivative of a certain function is how to compute this. And then if we kind of record all the steps that we're taking on the forward step, we can easily just compute the backward step because we have this memory of steps that we took. So, summing up this basic introduction into neural networks, loss functions, backpropagation, and optimization, neural networks are inspired by the way how human brains work. So it's a parametric model. We have our neurons that internally have certain weights, how we take the inputs and what we do with them. Think of the following. So if a neuron was saying, okay, it's in charge of saying whether this is a cat or a car, if it gets one neuron as input with the information of this is an eye, and another neuron of this is, I don't know, a tire or a windshield, then the neuron that is supposed to output the information of whether it's a cat or a car, or a cat in this specific case, so it's kind of the cat neuron, it will put a very high weight on the eye and a large negative weight on the windshield, thus being able to compute this in a really effective way. And these parameters are exactly what are being learned here. So we put a weight on each input, and to just put it back into your memory, the activation functions are there to introduce this non-linearity, because if you just have the neurons and you put one neuron behind the next one, which is just a multiplication, they would all collapse into a single matrix multiplication. So we need this non-linearity in between to not have that happen in our network. The model learns on the training set, and when we think about our training set, we also have the second part, which is our test set, where we actually want to see how well it performs. So the test set is something that the neural network has never seen before. The training set is what it is being given to fine-tune these parameters that it has. And the most important thing you should remember here is that they must have these two properties, that they must come from the same distribution and they should be independent from each other. The loss function then tells us how good we're doing, how well we're performing, how good our current parameters are. And what we usually do is we fine-tune these parameters, and we do that by gradient descent. That is our optimizer. So we're taking this loss, we're computing the surface, and then we're trying to take a small step into the direction that decreases our loss. And gradient descent is a very efficient way to navigate through this terrain to get to a really low point where our model performs really well. See you next week.